Section: Introduction. In this section, we introduce the importance of motion in video generation. Motion is crucial as it can transform a video from looking unrealistic to appearing professional. It captures attention, enhances storytelling, and shapes visual style. Renowned filmmakers like Kubrick and Kurosawa skillfully use motion to create engaging experiences. To produce compelling videos, we need realistic and expressive motion along with precise control. While text is the primary way we control video generation, it has limitations, especially regarding motion. Text can describe static scenes or broad actions, but it often fails to convey the nuances of motion. For example, a prompt like, "A bear quickly turns its head," can be interpreted in many ways, leaving questions about speed, trajectory, and acceleration. Even detailed descriptions may miss subtleties like timing or synchronized movements, which are better expressed through motion itself. Therefore, we explore motion as a complementary control method alongside text. We first note that to fully utilize motion's expressiveness, we need a representation that can encode various types of motion. We identify spatio-temporally sparse or dense motion trajectories as ideal candidates. These motion trajectories, also known as particle video or point tracks, follow the movement of points in a video, providing a rich encoding of motion. This representation can capture multiple points, represent specific object movements or overall scene motion, and manage temporally sparse motion constraints. Recent advancements in point track estimation have led to efficient algorithms that can process real-world videos for training. Given the flexibility of this motion representation, we refer to our motion conditioning as motion prompts. We train a control net on a pre-trained video diffusion model to accept these motion prompts. While these prompts can define various video motions, generating them practically can be challenging. Sparse trajectories, which indicate rough directions, are easy to create but lack fine control. On the other hand, dense trajectories offer precision but are difficult to design manually. To solve this, we observe that we can often translate high-level user requests, like, "Move the camera around the XZ plane," or "Rotate the cat's head," into detailed motion trajectories using computer vision signals. We call this process motion prompt expansion, similar to how we expand or rewrite text prompts in image generation. This method helps connect user intentions with our motion representation. We identify several scenarios where motion prompt expansion is effective, such as converting mouse drags into semi-dense motion trajectories, specifying both camera and object motion, transferring motion from one video to another, and enabling drag-based image editing. Although these methods are not yet real-time or causal, they suggest how users might interact with generative models and allow us to explore the generator's understanding of physics and world knowledge. Finally, we present quantitative results and human studies that show our model performs well compared to baselines. We also conduct ablation studies to validate our design choices. In summary, our contributions include focusing on motion as a conditioning signal, identifying motion tracks as a flexible representation, training a control net for motion prompts, proposing motion prompt expansion for detailed control, and applying our approach to various tasks. We also highlight emergent behaviors, such as physics understanding, indicating potential for probing video models and interacting with future world models. In the related work section, we discuss video diffusion models, which have shown impressive capabilities in generating videos based on natural language or animating static images. While they hold promise for creating world simulators, there is ongoing debate about their understanding of the physical world, suggesting the need for explicit physics integration. Our motion prompting technique enhances the flexibility and accuracy of specifying motion patterns in video generation and serves as a framework to assess a generative model's understanding of 3D or physics concepts. We also explore motion-conditioned video generation, where pre-trained text-to-video models can adapt to new motion patterns. Techniques like low-rank adaptation and dream booth can be applied for motion control. Recent research has focused on sparse, object-centric trajectory-based motion control, but these often require complex engineering for stable training. In contrast, we find that a simpler training approach yields high-quality results, allowing our model to handle a variety of tasks and motions without specialized engineering. Lastly, we emphasize the importance of selecting a suitable motion representation. While optical flow is common, it has limitations, such as error accumulation and poor occlusion handling. Instead, long-range feature matching or point trajectories are better suited for our needs, as they can manage occlusions and allow for both sparse and dense tracking over time. Section Summary. In this section, we emphasize the importance of motion in video generation and propose using spatio-temporally sparse or dense motion trajectories as a flexible representation for controlling video motion. We introduce motion prompt expansion to translate high-level user requests into detailed motion trajectories, enabling fine-grained control over various tasks while demonstrating our model's effectiveness through quantitative results and human studies. Section Method. In this section, we describe our video generation method, which takes a single frame, a text prompt, and a motion prompt represented by point tracks. We explain how to create these prompts in a later section, and full implementation details are available in the appendix. To effectively capture motion, we utilize point trajectories for our motion prompts. This allows us to represent various types of motion, whether sparse or dense, for single objects or entire scenes, and even account for occlusions with a visibility flag. This approach enables us to perform tasks like object control, camera control, simultaneous control, motion transfer, and drag-based image editing within a unified model. We represent a set of point trajectories as a three-dimensional array, where each point's two-dimensional coordinates are defined at each time step. We also track visibility with an array of ones and zeros, indicating whether a track is visible or occluded. Our model is built on Lumiere, a pre-trained video diffusion model that generates 5 seconds of video at 16 frames per second based on text in the first frame. To incorporate track conditioning, we use a control net that encodes tracks in a spatial temporal volume. Each track is assigned a unique embedding vector, which we place in the corresponding spacetime locations where the track is visible. We initialize the conditioning signal to 0 and update it based on visibility, ensuring that only visible tracks contribute to the signal. When multiple tracks occupy the same location, we sum their embeddings. For training, we prepare a video dataset paired with tracks by applying a point tracking method to a large internal dataset of videos. We extract a high density of tracks and predicted occlusions, believing that diverse motion training will enhance our model's flexibility. During training, we follow the control net approach, providing a conditioning signal to a trainable version of the base model's encoder and optimizing the standard diffusion loss. We sample a random number of tracks for each video to construct the conditioning signal. We notice that the loss does not correlate with the model's ability to follow tracks, and we observe a sudden convergence phenomenon where the model quickly transitions from ignoring the conditioning signal to being fully trained. Our model demonstrates strong generalization capabilities. Although trained on randomly sampled tracks, it can adapt to spatially localized track conditioning. It also generalizes well to varying numbers of tracks, whether more or fewer than those seen during training. Additionally, it can handle tracks that do not start from the first frame, likely due to the network's inductive biases and the variety of trajectories used in training. Section Summary. In this section, we describe our video generation method that utilizes a single frame, a text prompt, and motion prompts represented by point trajectories to capture diverse motion types. We detail our model architecture built on a pre-trained video diffusion model, the data preparation process using a point tracking method, and our training approach, which allows the model to generalize effectively across various track conditions and motions. Section: Motion Prompts. In this section, we explore various effects that can be achieved through motion prompts and their expansion. We identify and demonstrate several types of expansion, as illustrated in our figures. The text prompts and parameters for each video are detailed in our table, and we encourage readers to view the generated videos on our platform. Our model allows us to interact with images by using a graphical user interface, GUI, that displays a still image and captures mouse movements from the user. These movements are converted into tracks, which are then input into the model along with the initial image and text. For simple mouse movements, our method resembles previous work on video generation based on sparse trajectories. However, our model can also handle partial tracks, allowing for more natural user control, as shown in our figures. While we record mouse inputs in real time, generating the output video takes about 12 minutes due to the sampling from the video diffusion model. To create motion prompts, we translate mouse drags into a grid of point tracks. Users can choose the density and size of this grid, similar to how Gaussian blurring works, to define the motion's spatial extent. This grid setup occurs only during inference, not during training. Users can also place static tracks to keep the background still or allow tracks to persist after a mouse drag. We find that these interaction motion prompts can produce simple motions, like turning a parrot's head, but they can also create complex dynamics, such as moving hair or sweeping sand. These examples help us understand the model's learned physics and world knowledge. This suggests that we can use motion prompts to debug video models and explore their limitations, as discussed later. Additionally, as models improve, we might use these prompts to interact with video generation models as if they were world models. A practical application of this interaction capability is drag-based image editing, where user-supplied drags edit an image so that objects follow these movements. We present qualitative results in our figures. We can also reinterpret mouse movements as controlling geometric shapes, like spheres. By placing these shapes over objects, we gain finer control than with just mouse tracks. For instance, we can rotate a cat's head or a frog's eye by using a sphere, allowing for more complex motions than simple translations. Furthermore, we can design motion prompts for camera control. We first use a depth estimator to create a point cloud of the scene, then project this onto camera trajectories to generate 2D tracks. We can enhance quality with Z buffering for occlusion flags. Our model allows for camera movements, such as orbiting or arcing upwards, and we can combine this with mouse recordings for easier use. We construct camera trajectories that follow mouse movements while keeping the camera on a vertical plane. Notably, our model is not trained on specific camera poses, nor does it use pose annotations in training data. Despite this, we achieve effective camera control, demonstrating that we can train a model on general motions and utilize motion prompts to reveal specific capabilities. Section Summary. In this section, we explore various effects achieved through motion prompts and prompt expansion, demonstrating how user interactions with images can lead to both simple and complex dynamics in video generation. We also discuss applications such as drag-based image editing, object control using geometric primitives, and camera control through depth estimation, highlighting the model's ability to generalize and respond to user inputs effectively. Section: Composing Motions. In this section, we explore how we can combine motion prompts to enhance our capabilities. For instance, by merging tracks for object and camera control, we achieve simultaneous control of both. We convert object tracks into displacements and add these to the camera control tracks. While this method is an approximation in 2 dimensions and may struggle with extreme camera movements, we find it effective for small to moderate motions. Importantly, we do not specifically train for this ability, unlike previous studies. Next, we discuss motion transfer, which allows us to apply motions from one video to another image. For example, we can take the motion of a person turning their head and use it to animate a macaque. Our model shows surprising robustness, enabling us to apply motions to images that are quite different from the source. In one case, we transferred the motion of a monkey chewing to a bird's eye view of trees, resulting in a unique effect where the monkey is only visible while the video plays, due to a perceptual phenomenon. We categorize failures into 2 main types. The first type involves issues with our motion conditioning or prompting, such as when a cow's head appears unnaturally stretched because its horns are mistakenly locked to the background. The second type stems from limitations in the underlying video model, like when dragging a chess piece results in a new one appearing unexpectedly. These failures suggest that motion prompts could help us probe video models and identify their limitations. We also present quantitative results alongside qualitative examples. We benchmark our method against recent approaches and conduct a human study, detailing our experimental setup. For evaluating our video generation, we use the Davis video dataset, extracting first frames and tracks to feed into our models with generated text prompts. We test various track densities, comparing our method with image conductor and drag anything. We assess the generated video's quality using metrics like PSNR, SSIM, LPIPS, and FVD, and we measure how well the generated video matches the motion conditioning using endpoint error. Our results, shown in a table, indicate that our model outperforms the baselines in most cases. Although drag anything sometimes performs better in terms of endpoint error with fewer tracks, it also introduces visual artifacts, as seen in its lower scores for other quality metrics. We provide additional data for different track counts in the appendix. In our human study, we created a set of 30 inputs with single trajectories and conducted a 2-alternative forced choice test. Participants evaluated which video better followed the motion conditioning, which had more realistic motion, and which had higher visual quality. Our method was preferred over the baselines across all categories, as detailed in the results table. Lastly, we present ablation studies where we trained our model on sparse and dense point trajectories. We found that dense training is most effective, even for sparse tracks, likely because it provides a stronger training signal. We note that our evaluation numbers differ from previous sections due to using less data and fewer training steps for these ablations.